good morning, everybody. Welcome to week 2. In view of the nice weather, and since Bill Anderson will join us sometime during the day, I think we should try to do a conference photo. I'm not sure when, maybe in a coffee break, maybe during a lunch break. I might run out once during your lecture, David, to organize this.
Sure, okay.
But get ready. Pull your combs. Okay, David, please.
Okay. So last time I was telling you about the hierarchical lattice. It's a kind of nursery school for the renormalization group. And it points out some of the main features which you would like to duplicate, and in fact which can be duplicated for simple models on the Euclidean lattice. And the point I was emphasizing was the following structure for a Gaussian field, which are typical of massless Gaussian fields. Firstly, that you can write the Gaussian field as a sum of increments beginning at zeta 1 and zeta 2, which are Gaussian and which are independent. And secondly, that these increments have the property at a single scale j that zeta x and zeta y are independent if x minus y is greater than L. I've always had a weakness for getting confused between strictly greater and greater or equal, even though it's critical. And I might have written it as greater than or equal in the last lecture, but I think this is the right one. Third, that these increments are, statistically speaking...
Some power of L.
Oh, yes, thank you. Even more crucial. Thank you very much. That would make quite a difference. And thirdly, these increments are, statistically speaking, scalings of just one field. So I can write that by saying that the j plus 1th increment at x is in distribution the same as the jth increment at L inverse of x with a prefactor of L to the minus box phi. This is a very important number. This is the number which I call the dimension of the field phi. And you read it off from the Green's function that the field phi has. So if the Green's function, or the covariance of the field phi, falls off as a power minus d minus 2, then the dimension here, so if the covariance of the phi field, so this guy has covariance u of x minus y. Usually I write it as u of x comma y, but I'm a bit sloppy and sometimes write it like that. If that falls off as a power, then phi is half this number. And if you like to work in fractional dimensions, which the physicists do, they have a very neat and beautiful way of doing that by in perturbation theory. And this is not quite the same thing what I'm describing, but it performs many of the same functions. You can simply change that power to another number. And what those functions are will be easier for me to explain later on today, so don't worry about that too much at the moment. So we're going to work on so I'm going to take these as axioms for my Gaussian, or for my Gaussian field, and we're going to work on a big probability space which carries all of those increments simultaneously as random variables, so that I can write, before I was writing equals in distribution, but I can write it as an equality. And then the reason why I still keep this is a confusing matter in the last line, is because these fields are really different. I mean, I'm not claiming that, you could not claim that zeta of x j plus 1 is actually exactly equal to that, because then, of course, these fields would not be Gaussian and independent, which is what we're claiming. So all we're saying is the probability law for this is the same as the probability law for that, with this script d on the top. Now, if we define, I just want to rewrite 3 in a different way, which is actually something I did last time too. If we define a field phi sub j of x by the equation that it's the sum over the increment zeta sub k, but the sum begins at j plus 1, then we can re-express this last step here. Then 3 becomes something which I might call property 3 prime. We can say that, or 3 and 1 plus 1. We can say that this phi, well, since this sum begins at greater or equal to 1, this phi in terms of this notation is really phi 0. I don't put the 0 on it, though, because I want you to think of this phi as the field that we're really trying to analyze, and these are just auxiliary things. But it happens to be phi 0 because k greater than 0 is the same as this sum here. But this phi is equal to, and what you do is you just think of this as phi is equal to zeta 1 plus zeta 2 plus zeta 3, like that. And you call this lot here phi 1. That's the definition I'm making. So it's phi 1 plus the first increment, zeta 1. And then this last condition 3 here is telling you that phi 1 is up to a scaling the same as the field phi. So phi 1 of x in distribution has the same probability law as L to the minus phi box phi L inverse of x. And this is the best way to think of these for what I'm coming up to do next. This is the best way to think of axioms 1 and 3. It's giving you some interesting information about the sorry, this is actually true as an equality, about the field that you're trying to analyze. It's equal to a statistical copy of a scaling of itself plus an increment. This is a 1 here. Maybe I should leave this off because it was a semicolon, but it looks awfully like a J. Okay. Now, with that, we have this, I'll put Brydges down. We have this structure here is true both for the hierarchical model and for the Euclidean model, the way I've said it. For the Euclidean model with a lattice, okay, this last one is slightly, you have to take it as an approximate equality because of lattice effects, but just don't worry about that. Basically, these 3 axioms simultaneously capture the essence of the real model with a massless Gaussian, and also the hierarchical model. And so that's what I'm going to say, is that the hierarchical field actually is a field that has these 3 properties, and it does a few other things for you as well. So in the hierarchical case, this last axiom, that phi 1 is equal in distribution to this, tells you a bit more than perhaps is obvious. It tells you that phi 1 is constant on balls. So remember, hierarchical lattice, I'm drawing a one-dimensional one here, but of course we're interested in higher dimensions, had this kind of structure for the balls. And for the hierarchical lattice, L inverse was simply the operation of shrinking these balls down to a point. I think I didn't tell you last time what the group structure is on the hierarchical lattice, so I should mention that. This is something I should have said last time. Group structure. So you remember that for the hierarchical lattice, in this case, which was given by L equals 2, the points actually are binaries, are sequences of zeros and ones. Like this is 0, this is 1, this is 1 0, 1 1, 100, 101, 1 1, 1 1 0, 1 1 1, and so on. And the distance, so just to remind you, the distance between 2 points is the diameter of the smallest ball containing them. And to show you how to get those diameters, these balls are all of diameter L, and these ones here are all of diameter L squared, and the one above would be an L cubed ball. Now, it's nice that you can write the distance also between x and y as just simply the norm of x minus y, meaning the norm is just the diameter of the smallest ball that contains the point x minus y. But then in order to do that, you have to know what x minus y means. It doesn't mean quite what you think. I'll just illustrate what it means by adding or subtracting a couple of points here. So the group structure, for example, suppose we take 1, this point, and I want to add to it maybe that point, 1 1. So you regard them as sequences going this way, and I never can remember the right notation for this in group theory, but you should think of them as sequences which have infinitely many zeros to the left here. So basically what they are is the direct sum of Z2s, where all but finitely many entries are 0. And if you want to add it, you add it as a direct sum. So here and here you add it and you get 2, and 2 is the same as 0. And there you add it there. So you don't do any carrying. No carrying in this add. That's the difference, basically, between this lattice structure and the Euclidean structures. You don't do any carrying. So, and then the subtraction is the same way, and that tells you what the meaning of this is. Right, now, to do the renormalization group on this lattice, the renormalization group is actually not a group in this formulation. In Wilson's formulation, it's not a group, it's a semigroup at best, and that's what we'll see today. It consists of integrating out the increment zeta 1, and then rewriting the resulting object will then depend on phi 1, because phi is equal to zeta 1 plus phi 1. So if I integrate out that one, the resulting object will depend on phi 1, and then we put in this scaling law that phi 1 is related to the original phi that way, and we kind of come back to the same system, and we can do this over and over again, and that's each one of those is called a renormalization group transformation. What I was going to say before I got into this group structure is some other consequence that we'll need about this relation here. You see, in the hierarchical lattice, L inverse of x means contract these 2 points like that. It's a map from the hierarchical lattice to itself. But since it identifies points that are in the same ball, it means that this guy here has to be constant on balls, right? Because if you put 2 different points in here for the x, which are the same, which are in the same ball, they'll get identified over here. So the phi 1 is constant on balls. So I'll write that down like that. And another way of saying that they're in the same ball is if the distance between them is less than L. So any 2 points which are separated by distance L or less have a constant phi 1 field assigned to them. So here's the proposition. Very simple proposition, hardly worth it, in fact, but has the structure. We can take the expectation of I to the power of lambda, conditioned on phi 1, and if we do, we will get, again, a product structure, something called I tilde to the power of L inverse of lambda, where I tilde sub b is the expectation of I to the power of b given phi 1. Now let me just finish writing out this proposition, then I'll try to explain this rather abstract notation. The b here is actually got 2 different meanings depending on which side of the equation you're looking at. So b is a point in the image under L inverse of lambda. So it's actually, B is simply a point, remembering that L inverse maps the hierarchical lattice into itself. This is just a way of saying that B is a point, and that's the way you should understand what it means on this side of the equation. So it's a point or a site in L infinity. But on this side of the equation, I want you to remember that it came by contracting a ball. And so actually here it means the ball that you got by contracting it. And then everything makes some sense in this equation, even if you don't believe it, because I to the power of lambda, let's just squeeze in this notation here, I to the power of lambda means the product of a function I sub x over points x in lambda. And I sub x, this notation meant that I is a function of the field at x. So over here, what we're saying is take the product of the i's that are in the ball. And over here we're saying take the product of the i's that are in the whole universe, lambda. And then there's a second part, which says define I prime of b sub b by replacing by using this formula here. We'll replace the phi 1 by what it's equal to in law. So this guy here, this brings us back to what I tilde, so by replacing phi 1, by replacing in I tilde, should be phi 1 of x by this thing, which it's equal to in law. You see, what is the meaning of this notation here? You taking the expectation of I, which is a function of the field phi, conditioned on phi 1. It just means integrate out zeta 1. Hold phi 1 fixed, integrate out zeta 1. I think I'll try and squeeze this underneath. Concretely, taking the expectation of a function holding phi 1 fixed is exactly the same as doing the integral over zeta 1 of f of phi 1 plus zeta 1. So this guy is a function of phi 1 after you've gotten through integrating out the zeta 1. This guy is a function of phi 1, but then you define the I prime by replacing the phi 1 by this scaling equivalence. And this is what brings us back to almost to exactly the same situations we started in, so that we can now view the operation of integrating out zeta 2 as just a repetition of what we just did, because they're equivalent in scaling. So this is the very simple renormalization group structure of the hierarchical models. We can, well, I haven't finished this statement. We can take the expectation of I to the power of lambda in 2 steps. And those 2 steps amount to the equation expectation of I to the lambda is the expectation of I prime. My writing is very hard to read here, I'm afraid. Let me rub something out to make it clearer. I prime to the power of L inverse lambda. That's the conclusion. That's the second conclusion, that the expectation we're trying to calculate, expectation of I to the lambda, is equal to the expectation of a simpler object, I prime to the power of L inverse lambda. Why is it simpler? Because this box this lambda, which is a big ball, got shrunk by a factor of L. You shrunk all of the points by identifying these points in the lattice to single points. You make all the balls above kind of drop down one level. So we've made lambda much smaller than it used to be. If we repeat this over and over again, eventually we'll bring lambda to a single point. Then it'll be one integral to do. So let me make that point before I go ahead and prove this little theorem here. If lambda is a ball of diameter L to the n, then n repetitions of the map I goes to I prime. Notice what is happening here is I just need to know the I at a single point, and this operation here, together with the rescaling, brings me back to another I at this, also defined at a point. So this notation here, really I is a collection of I sub x's, where x is in the infinite lattice. But they're all the same at every point x, and so I only have to tell you what one of them is. And you know what all of them are. They don't actually have to be the same for this proposition to work. They can be different, and that's actually useful because, remember, we're trying to calculate the Laplace transform of one of these measures. And so in the end, I'm going to be calculating the ratio of 2 objects. The one on the top actually doesn't have I the same at every point, but for the purposes of doing this calculation at the moment, I'm taking the special case where they're all the same. So, n repetitions of this map generate, well, you can say that let's call I naught the first I that you're given. Then you get I1, I2, up to I sub n, which is simply means apply this map n times. And then we find that the expectation of I to the lambda is really just the expectation of I sub n to a single point. I want to write L inverse L to the minus n of lambda like that. You shrunk it L to the n times, but that's a single point. So it's the expectation of I sub n at the point 0, say, if we take lambda to be a ball of diameter Ln containing 0. So this is just an object at a single point, and this expectation integrates out the field which it depends on at that point. It's a one-dimensional integral. So presumably life has become very simple by that time if you've understood this transformation well. So let's prove this little proposition here, just to show you how easy this stuff is at this level. And also to bring out the contrast with the difficulties of the Euclidean case. So, starting with 1, I want to take the expectation of I to the power of lambda conditioned on holding the field phi 1 fixed. So as we've emphasized, that means we're just integrating out zeta 1, but zeta 1 has this independence property. This is where we're going to use axiom 2. So what I should do to take advantage of that independence is, well, looking at the hierarchical lattice structure here, it means that those two zetas depend on each other, and those two depend on each other, but for example, those two there and there are independent. So balls are independent. So what I should do is to take this product over points in lambda in 2 steps, write it as I to the power of a ball, and then take balls in L inverse of lambda. That's just a rewrite of I to the lambda, and take the conditional expectation of that. And then we can use the independence of the balls and just move the product outside. Independence. This is axiom 2. So then we will get the formula that I claimed, because we can so I'll just write the next line with it outside. It'll be the product of B inside L inverse lambda, expectation I to the B conditioned on phi 1. But this thing here is what we're calling I tilde. That's how I've defined I tilde of the ball B. So that's written in this messy proposition somewhere around here. We've defined I tilde that way. So we immediately see that we've proved that this expectation is a product of I tildes over balls in the L inverse lambda. That's what I'm writing here. So this is just I tilde raised to the power of L inverse lambda. And then for the second property, which is even more trivial, we just do the expectation of I to the lambda that we have on this side here in 2 steps. We write it as an expectation and then an expectation of I to the lambda conditioned on phi 1. So that's just probabilistic notation for integrate out zeta 1, holding phi 1 fixed. Integrate out zeta 1 holding phi 1 fixed, then integrate out all the remaining fields. What the probabilists think is that this expectation is actually also integrating out zeta 1 again. But it doesn't matter because it was already integrated out. So if you integrate it out again, it's a probability measure. You just get 1. So that's why they use the same letter E on both sides. So therefore, this is just going to be this outer expectation, and we can use part 1 to replace this by I tilde to the L inverse of lambda. So here we used part 1. Right. So at this point, we just have to understand, let me just make sure I didn't miss anything, we just have to understand this operation of defining I tilde this way, followed by the scaling, replacing phi 1 by phi. So let's try to first understand that. That's a nonlinear map, because it's nonlinear because you've got all these i's at different points. The ball in the lattice that I have there only has 2 points, but in higher dimensional lattices, you'd have L to the D points. You've got I at all these different points, depending on zeta 1 at each of those points, which are dependent fields, and you have to integrate out the zeta 1, this product, and the product means it's nonlinear. But we can linearize that map and study the linearization first, and that's the standard thing to do in dynamical systems. You've got a nonlinear map. I haven't yet defined a space on which it's defined or anything like that. I've told you what the formula for the map is, but I haven't told you where it acts. Never mind about that for the moment. You've got a nonlinear map. I mean, just think of it for the time being as mapping on some possible space of admissible i's. These are just functions of one field at a point. So it's functions of one variable is what it acts on. We have to choose that space later. But it's a nonlinear map, and what you do is you linearize it, and you hope that in the linearized form, all of the eigenvalues of the linearized map are well, either strictly bigger than 1 or strictly smaller than 1. That's a nice situation called hyperbolic. And then you can understand basically if the map has that property that 1 is missing as an eigenvalue, you can, so there's a gap, you can use the linear part of the map as a very good control over what the nonlinear part of the map will do. Let's look at that next. So that's why we're going to linearize now. There's a fixed point. If I is equal to 1, then I tilde will be equal to 1. From this formula here, if you put in 1 there, you'll get 1, and then this will be 1. I want to linearize around the fixed point. So to do this, I'm going to write I sub x is equal to e to the minus u sub x. I'll write it as the exponential or something, which doesn't look like much of a linearization, but never mind. And then the idea is, since we're working near ix equals 1, that u is almost 0. So to motivate this definition that's coming up, just think of the following thing. E to the minus the sum over points x in a ball of u sub x. Why am I looking at this sum here? Because I need to take a product of i's, and a product of i's is exponential of the sum of the logs of i's. So it's nicer to study the log when you're doing product operations. So we write it in terms of u. So we look at this sum. This is I to the b. And it's approximately 1 minus the sum over x in b of u sub x, if we're working at the linearized level. And then if we take the expectation, of I to the b around holding phi 1 fixed, take it through here, that will be approximately 1 minus the sum over x in b of the expectation of u sub x hold phi 1 fixed. And then at the same level of approximation, regarding u as very small, that will be the same as e to the minus the sum over x in b u sub x conditional expectation of u sub x given phi. Given phi 1. So this is a definition. The linearization of Rg. So Rg is the map I goes to I prime. The linearization of Rg is u goes to u tilde followed by u tilde goes to u prime, where these two steps are that u tilde sub b is the sum over x in the ball B of the conditional expectation of u sub x given phi 1, and u prime sub b just means replace phi 1 of x by L inverse of phi L inverse of x, like we always do. It's the rescaling operation at the end. This is an incredibly simple map, this linearization, as I will now show, because we were talking earlier about Wick-ordered powers, right? And Wick-ordered powers are just exactly what you need to understand this linearized map. Here's a little lemma. If we take u to be Wick-ordered power phi to the power of p, then u prime is also phi Wick-ordered raised to the power of p times the prefactor L to the d minus p times the dimension of phi. This is the significance of the Wick-ordered polynomials in the renormalization group. They are the eigendirections for the linearized renormalization group map. So just as a little exercise in remembering what we already did, I'll just prove a bit of this for you. Let's just look at u tilde sub b. U tilde sub b, formula up there, is the sum over x in b conditional expectation of phi to the power of p at x holding phi 1 fixed. So all I did here was to take my formula for u tilde of b, which is up there, and I'm doing the special case where u is Wick ordered power of, is Wick power of phi. So I just put that in. So what we really have to see is that taking the conditional expectation of a Wick ordered power spits back a Wick ordered power up to a multiple. And the interesting thing in this calculation is, where does the L to the D come from? That's right there. That's D stands for dimension, but D also stands for dangerous. So let's look. Remember that this is just integrating out zeta 1, and you have to write phi. I'll do two steps in one here. You have to write phi x plus zeta x to the power of p. So I'm using this remark here to take a conditional expectation of f with phi 1 fixed. You put into the argument of f phi written this way. Phi is phi 1 plus zeta. And you hold phi 1 fixed and do the integral over zeta 1. So I'm doing the integral over zeta 1. I've done all of that. But there is this Wick power here, right? I haven't put that in yet. So let's put that in now, remembering the definition of Wick power. It was applying a minus 1/2 Laplacian. Now, which Laplacian is this? This Laplacian was one of these d by d phi's, well, d by d zetas, I guess you'd have to write here. It doesn't matter whether you write phi or zeta, because it's the sum of the two of them. It doesn't matter which one you differentiate with respect to. And then there is a covariance that you put in here. And the covariance you put in, so I wasn't very explicit about that here, but the covariance you put here is the covariance of that field phi. Let's call it u. Where u, being the covariance of the field phi, you remember that I told you last time that the covariance of this field is going to be the sum of the covariances of all of those. So it's the sum of CJs. Starting at 1. Now, Wick's theorem enables you to do this expectation by thinking of it as e to the 1/2 Laplacian. But this Laplacian must have the covariance of zeta 1, which is C1. And then we have this one. And then we have this combination to the p. And you remember that Wick's theorem requires you to set zeta equal to 0 afterwards, right? Well, one neat way of writing that is not to put the zeta in at all, but just take all of these to be derivatives with respect to phi. That's the same thing, because differentiating with respect to phi is the same as differentiating with respect to zeta, and putting zeta equal to 0 you can do at the beginning if you change all the derivatives to phi derivatives. Now, what about this? Can you see what's going to happen? Laplacian sub c, 1, and Laplacian sub u, but with different signs. And if the u is the sum of the c's and the u occurs linearly, as it does in this Laplacian, what's going to happen? When you put them together, the c1 part is going to cancel out, right? So you're going to get the sum over x in b of e to the minus 1/2 Laplacian sub, I'll call it u1. u1 is the sum of zeta of Cj's where j begins at 2. Well, I always write it as strictly greater than 1 before. It's just, in other words, it's u minus C1. So that C1 cancelled part of that u there, and we've got phi sub x to the power of p. And then we realize that that is just the definition of what? The Wick-ordered phi sub, this is phi. I should have written phi sub 1 here. It's a bit awkward. Sorry, phi sub 1x. This is phi sub 1x. These are derivatives with respect to phi 1 or zeta 1, but let's do them with respect to phi 1. And this is a phi 1 x. So we've ended up with a very canonical looking conclusion. It's the Wick-ordered phi 1 field at x to the power of p, and the Wick ordering is natural in the sense that it's the u1 covariance, and u1 is the covariance of phi 1. So we keep this structure that you started off with it being Wick-ordered with respect to its own covariance, and it ends up being Wick-ordered with respect to its own covariance. So it's nice that that one and that one match. That's good. That's in a way why I didn't bother to write in the Wick ordering, because it's always with respect to the field that appears inside, the covariance of the field that appears inside. Now, we haven't yet done the last step of the renormalization group map. We've gotten from here to here. And the interesting thing is that the expectation didn't appear to do anything in this clever notation. It just changed the Wick ordering. That is something, actually, but that's all it did. But now we have to put in the scaling. So that's u tilde. So u prime sub b. Now this is where I'm just going to tell you the answer, because I want you to check it for yourself, but it's almost hard to believe it can't be right. You see, everything depends on scale 1, and rescaling, we've got the statistical equivalence that up to a scaling scale, every scale 1 object is a scaling of every scale 0 object. So all that can really happen if I do the rescaling is that scale 1 will go back to being scale 0, both here and there. But you will get these very nice factors out front. You'll get that wonderful factor out front. So you can understand why a minus p phi is going to appear as a result of rescaling. Each field phi will get that factor out in front because of the rescaling. Where does the d come from? Well, we have this sum in front, right? So far, nothing in this calculation has actually used the hierarchical model. It's completely the same in the Euclidean and the hierarchical case. But now we use the hierarchical case. The fact is that phi 1 of x is the same field for all these points x. So the sum is just take all the terms that are here, and there are L to the d of them in general, 2 for that lattice there, but L to the d in general, and put phi sub 1 to the power of p, and just pick your favorite point x. I'm writing u sub b, you see, because b is the equivalence class of all of those points. It's the ball that contains them, so you can write b if you want. There's where the L to the d comes from, that sum. That's an expanding factor, which could be dangerous. But then the rescaling kind of comes in and, like a cavalry, and saves you a little bit. U prime is L to the d minus p like that. So that's all very nice. Now, how much can this rescaling here save you from the d? Let's look at that. it's a linear map, this map from U to U prime. So if I want, I can take as my initial U a sum of these things. And all that will happen is that each one will become the image. So if we start with, so that's the end of the proof. I mean, I didn't do the details in this last step here of the rescaling, but that's the end of the proof modulo those details. But now, yes?
Sorry. David has spoken for 50 minutes now.
And no one asked a
Have we
question.
had a single question yet?
They're very sleepy.
It is Monday morning, isn't it? And the weekend was a lot of fun. I think part of it is David's brilliant delivery. He's extremely clear, and not too many questions arise in the first place. But you're not convince me that all of you have understood everything the last 50 minutes. I think this is almost surely not true. With probability 1, there was one or several of you who did not understand one or other point that David made.
I bet, in fact.
So this is why I'm getting up.
Most of you didn't understand the notation, I bet.
Remember, the lecturers are not at their service, but at your service. The lecturers come here well prepared. David is extremely well prepared every time he takes the floor. But to turn this into a success, we need your participation. I want more action. I want you to get into this. And I don't want you to ask just questions for the sake of it. But I trust there must be questions in the audience. And last week I spent quite some time asking them for you. But don't think that I'm going to do this again this week for you. Maybe a little bit, but by now you should have understood the point of this exercise, and you should be in it. And let's just get on with it. Wake up. Okay, so you had 50 minutes to sleep, but that's it.
So now I hope you're all ashamed of yourselves. Okay, notation is completely crystal clear, even for physicists who don't like expectations and equal in distributions and so on. I'm sure it's not. But I will go on unless someone asks me. Yes?
Perhaps you're coming onto it, but you remarked that D also stood for danger.
Yes.
Should that be clear by now already, or is that?
No, but you can see that the L to the D is a factor that's going to be, well, it's 2 to the D in the case of the simple lattice I produced there. Well, 2 to the 1 actually, it's just a factor of 2. D is 1 in the lattice. So you can see that you see the linearization argument is based on the idea that U is small. Now, will that remain so? If I apply this map over and over again and I have an expanding direction in it, which is this D here, then I'm in trouble with that hypothesis that I can study the nonlinear map by linearizing it. So that is very dangerous, that D.
So I was your interaction, U was interaction of the logarithm of the interaction.
Exactly.
And this notation, big U is, or double point title PU means that the weak ordering of the P power of average over U, or the expectation value of the interaction.
So this guy here is the Wick ordered power, which is just a polynomial, as they say, right? And it's defined, so remember that that's defined as e to the 1/2 the Laplacian U with a wrong sign there, acting on phi to the p. That's the way I did it earlier. And the subscript U is telling you, yes, that's very confusing. I'm having great trouble with my subscripts because sometimes they're points in the lattice, sometimes they're scales J, and here it's neither one nor the other. It's trying to tell you that that's how you normal order. And so perhaps it is better to leave it off. And just, you have to remember that the guy you put there is the covariance of the guy that you have there in all cases. And you should stop me when the, yes, I mean, here we have scale 1, point x, right? That's what that notation means. And to pick you all up at this point, now that you've had your nice nap, what we now know, as a result of all this calculation, is that the linearization, as you can have a picture like this. I can only draw 2 directions on the blackboard, but I lives in a space of functions of the field, so there are infinitely many directions. And there's a fixed point, which we generally draw at the origin, but it's actually the function I equals 1. But it is okay to think of it as the origin, because it corresponds to u being 0, because I is e to the minus u. So there's a fixed point u at the origin, and we are trying to understand what will happen to points, at least in a small neighborhood of that. And there's a nonlinear map acting on the function I, which is this renormalization group transformation. The renormalization group transformation is simply take the points, the interactions I that are in a neighborhood of a point x, multiply them all together and integrate out zeta 1. Then they become a new interaction for the whole block. The phi, in renormalization group terms, phi 1 is the block spin field, and zeta is the fluctuation field. If you're doing this in momentum space, as you're used to in theoretical physics, you're integrating out the high momentum part when you integrate out zeta 1, and the block spin is the low momentum part.
David,
Yes.
I equal 1 is obviously, yes, the fixed point as you showed.
Yeah.
But is it obvious? Because this is a linear map in general, so is it obvious that this is the only fixed point?
No, it's not obvious that it's the only fixed point. In fact, the most interesting cases would be when it isn't the only fixed point. But unfortunately, it's the only fixed point that's easy to study. And so that's the one I'm beginning with. Right, yes. Yes, indeed. So, I said I was going to concentrate on the case where the scaling limit of the theory is massless Gaussian. And so that means that you're looking at I equals 1 as the fixed point. I'm doing this because it's not very exciting for physicists to study the Gaussian fixed point, but there are mathematicians here as well, and it's already an incredibly hard exercise to study the Gaussian fixed point on the Euclidean lattice. So we have to understand that at the first to begin with. So what we're just seeing here, each phi, each Wick-ordered Wick power is a direction in this big space of functions. And obviously, if p gets large enough, this p phi will overpower the d, and then they will start to contract. So there are infinitely many contracting directions, but there are going to be finitely many expanding directions, probably. We'll look at each dimension in a moment. I am assuming, again, to make life easier, that the dimension of the field is strictly greater than 0. This rules out 2 dimensions, because you remember back here, d minus 2, if d was 2 dimensions, then the dimension of the field is going to be 0. So 2-dimensional theories are even more interesting in a way, because there are unbelievably many directions that don't contract, that expand, or it might expand. So let me go on a little bit then. What I want to do then is to take a sum of these. So this is a linear map, this transformation. U goes to U prime. U goes to U prime is linear. So we can take as our initial U a sum, lambda sub p, phi Wick-ordered powers over p. That's a finite sum. I only want to consider polynomials to begin with, but in fact, I guess what I'm saying is also completely fine if it's an infinite sum and it converges in some sense. The right way to talk about convergence in that case would probably be L2 convergence. Never mind about that for the moment. Anyway, we have U. If we have a finite sum, then U prime, so if then u prime will be a sum over p lambda p, and then you'll have this factor L to the d minus p times power of phi, Wick ordered phi to the p. So you see, the linear map is extremely well expressed when you use these Wick ordered powers, because all it amounts to is changing the coupling constants. So you start with u is some linear combination. These are called coupling constants, these lambda sub p, some linear combination of powers, Wick powers, and u prime after the linear application of the linearized renormalization group map is just lambda prime times phi to the p with some different coupling constants. And we write the formula for lambda prime, we can understand the expanding and contracting directions. Lambda prime sub p, the coupling constant in front of the pth power is L to the d minus p phi lambda sub p. So let's look at this with various dimensions where phi, let's put in what phi is. The canonical choice for the dimension of phi is d minus 2 over 2. So then, let's just, for example, look at lambda 4, the coefficient of Wick power phi to the fourth. The reason why I'm looking at that is because in this sum here, p can start at 0, which means I have a constant term. Wick ordered phi to the 0 is just constants. So there's a constant term. Let's take the case where u is even in phi. Then there'd be a phi squared. That wouldn't scare me too much, even if it does grow, because it's Gaussian, and I might be able to stick it in with a Gaussian measure and calculate exactly with that. But phi to the fourth would scare me if it grows, because that's certainly not Gaussian, and I don't know what to do with it if it gets too big. So that's why I'm looking at that. Lambda 4 is equal to the lambda 4 you started with, and then you take this d and you put in p equals 4 and you put in those numbers, and I think you come up with d 4 minus d. So now we see the great significance of 4 dimensions in theoretical physics. We didn't know it before. If d is bigger than 4, this thing will die under the renormalization group. If d is smaller than 4, it will grow under the renormalization group, meaning that problems in 3 dimensions and certainly 2 dimensions are, from the point of view of the renormalization group, much more difficult than problems in more than 4 dimensions. When d is exactly 4, this thing is said to be marginal. So there is this classification. Relevant. This is for the mathematicians. That means that lambda p prime expands. And the object that's said to be relevant is the Wick power phi to the p. So if p is, in this case, p is 0, 1, and 2 are relevant powers of phi to the p, because those will expand. You can calculate, let's just do lambda 2 as well. Lambda 2 prime always turns out to be L squared in every dimension times lambda 2. When you put in, so I'm just saying take d to be anything you like, take p to be 2. When you take p to be 2, the d over 2 gets doubled and cancels the d, and you're left with a 2. This is, in fact, the coefficient in front of phi squared. And phi squared in physical terms as the mass, it sets a length scale for exponential decay. And that's why it grows as L squared. It's actually the square of a length scale. So it grows as L squared, and it's telling you that if you take an exponentially decaying theory and you back off from it and look at it from further and further away, it will look smaller and smaller and smaller at the rate of L squared. Or L for each time. So decay lengths shrink when you look at them from far away. That means that massive decaying excitations become invisible in the scaling limit. You can't see them anymore. They become point-like. So these are the relevant directions, and then there's irrelevant. These are the contracting. Lambda p contracts. In this case, it's going to be p is greater than, for dimension 4. In dimension d greater than 4, everything phi to the 4th, phi to the 6th, and so on, all contract.
But you left out the 3, the relevant ones.
I did.
The 1.
I did because I want to look at even interactions only.
1 is not even either, is it?
1 is even. Right. Thank you. Yeah. P is 0 and 2. Even. So let's just look at even case. Even U. Well, you can look at the other ones too. For example, phi cubed. You'll find that a phi cubed interaction is relevant in dimensions less than 6 by this formula. So this is very good. This is telling you what might end up dominating the scaling limit. This kind of classification. You can take it a lot further. Now, of course, in dimension d great equals 4, phi to the 4th is called marginal. So marginal lambda prime sub p is the same as lambda p at the linear level within linearization. Phi to the 4th, therefore, is marginal in 4 dimensions. Now, the idea, just to come back quickly to proving scaling limits are what they are. Let me just remind you what the dangerous problems there were and how this might help us. So in the last lecture, I did this little trick of translating the Gaussian field. And so we were said I want to calculate the Laplace transform with a scaling in it. The scaling that I want to put now is going to always be of the form L to some power. So it's perhaps not all L's that we can study the limit, but just a particular sequence in this model. And what I did was I did a translation in the field to bring out the part which I hoped would be the Gaussian, would be the scaling limit. So that was e to the 1/2 f sub L u f sub L. That term comes about by pretending that I is 1 and just doing a Gaussian evaluation. And then we had a ratio, expectation of I, which was translated to the power of lambda, divided by expectation of I to the power of lambda. Now, under the renormalization group map, we can keep replacing the object on the top and the object on the bottom by exactly the same objects, and lambda shrinks. That's the point of one of the points we're saying up till now. Within the linearized level, what we see is that there's a dangerous number, lambda 0, which is the multiple in front of the constants, which keeps expanding by a factor of, since p is 0, keeps expanding by L to the d. Now, you remember that I remarked to you earlier that this, in mathematical terms, is very, very difficult, this cancellation, because the thing on the top is of order exponential order to the lambda. And the thing on the bottom is also e to the order lambda. And you have to make that cancellation exactly in order to understand what we're getting as a result of, well, just to do the infinite volume limit, where lambda gets large. But it's very easy to make that cancellation, at least the linearization suggests it will be, because it just says cancel out the lambda naught at each stage. The lambda naught that you get on the bottom, multiplying after each renormalization group step, if you have a lambda naught on the bottom, the lambda naught will actually be the same on the top, because all I did here is it's as if the effect of the tau is like adding one more field on at the very end. You've got zeta 1 plus zeta 2 plus zeta 3, and it's like having a last field added on, because it just translates it. So it has exactly the same structure, and under the linearized map, at least, it will map in exactly the same way, and you just cancel out e to the lambda naught times b, or times lambda, actually, at each step, at each RG step. Let me say cancel out e to the lambda naught factors at each RG step. And this, I'm going to put a big exclamation mark here, because it's a remarkably easy solution to a problem that looked totally frightening to begin with. They just cancel out. And that actually happens at the nonlinear level, because the nonlinear level will be to write I in a slightly more complicated form than e to the u, but there'll still be this e to the lambda naught multiplying as a factor that you can cancel out top and bottom. Now, for this reason, I'm not going to pay any more attention, actually, to lambda naught. I'm going to just systematically ignore it in the rest of today. If you want to prove that this is that this has a limit as script L goes to infinity, and remember what we've done now is we've taken the diameter. I said I want to take the diameter of the box lambda also to be L to the n. So we take n to infinity and do both the scaling limit and the infinite volume limit at the same time, which is a bit of a cheat. What you want to do is to show that this goes to 1. Now, if you're in more than 4 dimensions, it looks like you'll be able to do that, because in more than 4 dimensions, the lambda 4 will go to 0, and all of the higher powers will go to 0, and actually all you'll be left with something Gaussian on the top and the bottom for the I. But that could be very dangerous, because that could be a big Gaussian, and it could be annoying. Let's look into this, into the possible scaling limits. So there's various cases that can happen. So so this is still within the linear approximation. So 1, you might start off with lambda 2 initially greater than 0. And lambda 4 also greater than 0. And both small. If they're not small, then, I mean, within the linear approximation, it doesn't matter what they are. We can see what the result will be, but it's only if they're both small that the linear approximation will have anything to do with the nonlinear case. Now, what will happen here? Well, lambda 2 is relevant and it will grow. So there'll be a big coefficient in front of the phi squared. Lambda 4 is irrelevant. This is going to be for dimension greater than 4 for the moment. lambda 4 is irrelevant and will die. And so your initial interaction will evolve into a thing that looks like this. A very steep parabola. So I'll say that as e to the minus lambda 2 phi squared takes over. So the phi squared becomes dominant. Let's leave that case alone for a second. Case 2, lambda 2 initially less than 0, lambda 4 greater than 0. Okay, your problem. What's going to happen in this case according to the linear approximation? Lambda 2 is negative mass. Lambda 4 is positive phi to the fourth. Under the renormalization group, lambda 2 becomes what? Large negative, right? Lambda 4 becomes very small positive. So what is the potential going to look like? It's going to look like a monstrous double well. That's what you get when you get a small phi fourth competing with a large minus phi squared. And it's always expanding, you know. So to pay homage to Sidney Coleman, you'll get the double well doubly well. Now, the only case actually which yields a scaling limit in the sense that I've defined it, namely that this limit should exist as L goes to infinity, with the scaling that I proposed for you last time, which was canonical scaling, the only case is when the lambda 2 is 0. And you better take lambda 4 greater than 0, because otherwise it would be unstable. The linear approximation would still exist and you could calculate, but it wouldn't have anything to do with the nonlinear one. It would be unstable. That's trying to do an integral of e to the plus phi to the fourth. So in that case, lambda 2 stays 0, remains 0. Lambda 4 goes down to 0, and I maps to 1. And if I maps to 1, then the translate of 1, you know, it depends in exactly what topology or what sense you have convergence, but any reasonable sense which you define your convergence, if the I maps to 1 with some slight uniformity, then the translate of I will map to 1 as well. You'll get 1 over 1, and the scaling limit exists and is what you want, namely Gaussian. So that's actually the only case in which scaling limit exists as we've defined it. Now, the other cases, basically what's happening is that other operators are taking over. For example, here, you could start with a very small mass, and in which case this kind of a picture remains somewhat valid for many, many steps of the renormalization group. But ultimately, that mass is going to become large. And when that mass, this is called crossover, when that mass becomes large, you're doing the wrong scaling to get a scaling limit. I proposed, when I defined the scaling in F for you, I defined it under the supposition that the grad phi squared part of the massless Gaussian was going to be dominant in the scaling limit. But what we're seeing here is that it's not dominant in this case 1. Phi squared becomes dominant, and if you want to get a limit, you have to redefine the scaling so it's appropriate to phi squared, which is central limit scaling, and then you will get an independent, the scaling limit will be an independent Gaussian field at each point, called white noise sometimes. So this case here, you need to take into account that the, well, this is the two-phase region. What's happening here is the interaction, as I'll explain next time, is becoming not ergodic. It's splitting into two components where the phi is concentrated in one well or the other well. So that requires totally different scaling. Now, what about there are two things that I could tell you at this point, but I won't perhaps have time for both of them. One is, how would this scheme translate into the Euclidean world? Why does it roughly work the same way? So this is like rigorous renormalization group remarks. And the other is, what happens to the 5/4 in 4 dimensions? I put in the notes what happens to the 5/4 in 4 dimensions, and I think I'll just summarize it. You have the tools to work it out. That's why I wanted to do it. Let's see, I can rub out maybe this now.
David, are you going to say what goes on beyond the linear approximation? Or?
That's what I was going to try to do. Well, that's what I want to do next in the remaining 10 minutes. And we're at a bifurcation point now. There are two things to say what goes on beyond the linear approximation. We can calculate within perturbation theory to find out, for example, in 4 dimensions, where lambda sub 4 is marginal, what it really does because of corrections which are nonlinear. This is quite familiar to theoretical physicists. And so beyond linear approximation, and I guess I'll ask Tom's advice here. Do you think I should do 5/4 calculation in perturbation theory for these guys, or should I show them why this scheme also works in the Euclidean? In other words, a rigorous remark.
I don't know. I don't think you can do it in 10 minutes.
I can do something in both in 10 minutes.
Okay, well.
This is not the standard way of setting up the hierarchical model that I've given you, and the reason is because I wanted to say that it is very similar in the Euclidean lattice. There's a way to do the Euclidean lattice that looks very similar to this. So if you want to hear more about that, you can read about my Park City lecture notes, where you'll get more than you want to know about it from there. I will pass on the rigorous renormalization group and just talk about perturbation theory. Because this also has useful things for the mathematicians here in it as well. I just want to point out the following thing. d mu c1 e to the minus p. Suppose you want to evaluate an integral like this, and we do, because we've written I as e to the minus u, I sub x. And then we have I to the power of b is e to the minus some u sub x. And we're taking the case where u is a polynomial, and that polynomial is p. And we want to take the expectation, the conditional expectation of I to the power of b. So that means we want to integrate out zeta in a polynomial that depends on zeta. And up until now, I've been doing, the trick I've been doing, which is a linear trick, is to just put this integral up there. It's actually a lower bound by Jensen's inequality, but I've only said it's an approximation. But we can do a little better than that. So at the level of asymptotic series, which means that they don't converge, but if there's a coupling constant like alpha in front of p, it's asymptotic in alpha, what I'm writing down next. You can expand the exponential. And it's the interchange of the sum over the expansion of the exponential with the integral over zeta that makes this a not convergent series. It stops being convergent when you try to interchange, but it remains asymptotic. So we have this as an asymptotic series, and now you can evaluate this by Wick's theorem, right? And if you do, you will get p's hooked together into graphs. Let me draw a...
Are you taking p to be 5 to the 4th now, or?
Any polynomial. Yeah, the only thing, of course, that I would like is that p should be greater than or equal to 0. For this remark, any polynomial works. So when you use Wick's theorem on this, I want to explain a remarkable theorem called the linked cluster theorem. If when you use Wick's theorem on this creature here, you get graphs which I'm schematically drawing like this. What I mean here is that there are two lines joining a p to a p. You see there are n p's here. There are two lines joining a p to the p, and then there's a separate pair of p's, so this is like an n equals 4 term here, joined by a line. But what I'm trying to say is that they're disconnected, right, as a graph. There's this part and there's this part, and they don't have lines between them. So here's the thing that always astonished me when I first saw it. If you want the log instead of d mu c1 e to the minus p, do exactly the same graphical expansion that Wick's theorem generates here. Use exactly the same combinatorics for computing the value of each graph, but only keep the connected graphs. So it's a combinatorial miracle. So if we look at the result of the graph, so now I will think of phi to the fourth. I've written these graphs and their values out fairly carefully in the notes, so you can look at it afterwards. But here I'll just summarize in the last minute what we get. The logarithm of e to the minus phi to the fourth, which is the nonlinear renormalization group map, has graphs that look like this. Let's write out what this one means just to show you what's happening. There is a phi 1 which is squared and at a point x and Wick ordered. Well, actually it's a phi x, because I'm going to do the let's not do the rescaling. Phi 1 x, which is squared. There's another phi 1 at another point y, which is squared and Wick ordered, and these points x and y are summed over the block B, because I want to do here the sum over x in B of minus this, and let's put in a coupling constant lambda 4. And then the two lines are covariances C1 xy squared, and there's a factor which I think I have to read off in front, which is lambda squared over 2 over 4, where the 4 comes from some edge automorphisms and even point automorphisms. Now, remember, phi 1x is the same as phi 1y, so this is actually a phi 1 squared again at the point B, which is the equivalence class of x and y belonging to B, times something. Call it beta. And there's another contribution from here to phi to the fourth, but that's a phi to the fourth when you write it out. So when you're a bit more careful about second order perturbation theory, you find that lambda prime is equal to lambda 4. This is in dimension 4. That's the linear part. That term there is just a single phi to the fourth, which is the linear approximation I've been talking about up until now. And this is a correction to the linear approximation. Lambda 4 squared. Now, this recursion tells you that lambda 4, as you march through the scales, goes down as 1 upon j. You can solve that recursion and show it goes down as 1 upon j. So it's a very, very slow approach to 0, but lambda 4 in this more refined sense is actually contracting. And so that means that even in 4 dimensions, the phi to the 4th will go away. That's where I want to finish. I left no time for questions.
So?
What about the second diagram?
This one. That one, you mean? That's a very interesting diagram. That is a phi. This one? Ah, that's a phi cubed, right? A phi to the 6th. Where are you? I lost you. There, thank you. Now, phi to the 6th is irrelevant in 4 dimensions, right? So even though it's created by this operation of doing the renormalization group in a more accurate approximation, it will stay small because it's created and then it's driven down by this linearization effect. But it's showing you why you can't stay just within the class of e to the minus a 4th order polynomial. You need a space of functions. You have to define it on a space of functions. Many people have worked on the renormalization group. I'll put a lot of references in, but I don't want to go through them now.
Why is it of this order?
Why is it 6?
Why is it up to the 6?
Because it is, that's because what it is phi 1 plus zeta to the power of 4, and then phi 1 plus zeta 1 to the power of 4. So that's what each one of those is a polynomial p. But then it gets the effect of the line means differentiate with respect to zeta, and put in the covariance. And now you see it, right? Phi to the 6th.
I can see why the last one you were saying is interesting.
This one here is phi squared. So that's a correction to the mass. And it means that the true critical mass is not 0, like I claimed here. This was case somewhere around here. It was case, maybe I rubbed it off. Here it is. Within the linear approximation, lambda 2 is 0, but not within the nonlinear. It's slightly non-zero. It's of order the initial lambda naught squared. Because you have to adjust that so that the mass doesn't grow.
Will you discuss the real Euclidean case next time? Or?
No, next time what I want to do is talk about broken symmetry. So your chances to buttonhole me on other things like that are now over unless you want to catch me outside and
If
copy.
you start from case 2, right? Case 2 leads to symmetry break.
Yes, but I won't. I want to do symmetry breaking in a much less hammer and tongs method.
So maybe just one word on difference with Euclidean case. So what are major difficulties with this scheme?
If you see, just one word. Where's my eraser? I need an eraser to say.
First of all, on the hierarchical lattice, you can do everything recursively, right?
Yeah, you can, and it's been done by 3 or 4 different groups of people very nicely. On the non-Euclidean, so if you look at the form, for the Euclidean lattice and for the hierarchical, I'd actually work with a slightly more general form of the interaction initially. This is this is the relevant part, e to the minus lambda 5/4, for example, something explicit, which we can calculate exactly within the linear approximation. This is supposed to take up all the errors, the Taylor remainder terms. And you write it, if you expand it out by the binomial theorem, you get something like this. And if I draw a picture of a particular term, there are points in the lattice which are occupied by k's, which I'm drawing. and the points I'm not drawing are occupied by I. Now, if you imagine that we can deal with I exactly in some way, that's why I'm not drawing them, the question of what to do on the Euclidean lattice is whether you can handle this. And there is a natural way to do it, because when you go to the next scale, it will split into connected components. And those connected components, in the next scale, the blocks are of size L. So actually, I'd have to glue those two together into one bigger object. But the connected components still factor, and that's the key to doing the Euclidean case by these methods.
One also can do it resolutely.
Well, 5/4 has not been done. Well, strangely enough, 5⁴ with epsilon not 0 has been done by these methods. The epsilon, the dimension, in other words, is not canonical, giving us constructing a nonlinear fixed point. By these particular methods, 5⁴ itself with canonical dimension has not yet been done, although it has been done by Gavetsky, Kupian, and other people using a different style of renormalization group.
Right, let's go to coffee and be back at 11 for the next lecture.